In this video, I'm going to finish up my discussion on this chapter from the book I'm using, which is Organic Chemistry by L.G. Wade. And I'm looking at the 7th edition here. And so this is a chapter on stereochemistry, and so I'm going to finish that up here. And so I'm going to talk a bit about enantiomers, then I'm going to talk about diastereomers and conformers, and so kind of covering up a large array of topics here. So the first one is the chirality of conformationally mobile systems. And so if you look at something like this hexane structure here that's in this chair conformation, that looks like it is it's in chiral. And so if we take the mirror image of it, we get this. And if we took that and tried to rotate it around in 3D space, we would not be able to get back to this right here. And so those look like enantiomers. However, these are interconverting rapidly between the two conformers. And so remember, these chair conformations are called conformers. And so it's interconverting rapidly between them. And so you would essentially have like a racemic mixture of both of these conformers. And so a molecule cannot be optically active if its chiral conformations are in equilibrium with their mirror images. And so this structure here is not considered chiral because it's rapidly interconverting between these two things right here. And so to determine whether a conformationally mobile molecule can be optically active, consider its most symmetric conformation. And so that's actually what I have right here. So if we look at its most symmetric conformation, that's just with the 6-member ring flat. And so we see that this actually has an internal mirror plane of symmetry here. And so that is going to not be considered chiral. So inherently chiral compounds have no achievable achiral conformations. And so this is not inherently chiral because there is a conformation of it that is achiral. And so this cannot be a chiral compound here. And so we do not consider this chiral, even though in these chair conformations it appears chiral. And that's because it's able to switch between them. And so there's an equilibrium between the two of them. If you somehow took a bunch of these ones out, we would sort of by Le Chatelier's principle end up with a bunch going over here, and so it would reestablish that equilibrium. And so we can't really differentiate between the two of them. All right, and so here, this is just looking at, well, this would be a butane here. And so we see that if we're in the gouge form here, that it's chiral. If we're in this gouge form here, it's also chiral. But we can get it into an achiral conformation. So that is the totally eclipsed one here, which is achiral. And so again, we don't consider the butane to be a chiral molecule because it does have a form that is achiral. All right, so we can continue looking here at chiral compounds without asymmetric carbons. And so this one I thought was kind of a fun structure here because what we have is these bromines here and these iodines here, which are too big to allow this to sort of interchange between the two conformations. So this right here and this right here are actually considered different compounds because if we try to sort of if we try to rotate this around this bond here, so if we're trying to rotate around that bond here, these bromines will run into each other and these iodines will run into each other, and so it cannot interconvert and become this one right here. And so like I was saying above, if you took out one of those chair conformations, one of those chair conformers, it would quickly reestablish equilibrium. Where here, if we somehow were able to like remove this one from solution, this one right here would not actually be able to reestablish that equilibrium. And so this structure here is actually considered to be a chiral molecule. We also have these dienes here, so these are also chiral. And that's because these double bonds here do not allow for rotations around the bonds. And so if we took this structure right here and sort of swiveled it, 180 degrees perpendicular to the screen, we could end up with this right here superimposing on that, and this hydrogen right here so superimposing on that. But then we would end up with this hydrogen here pointing into the screen and this methyl group here pointing out of the screen. And so there's no way to superimpose those. And so even though this 2,3 pentadiene does not contain any chiral centers, it is a chiral molecule. So yeah, this is just the orbital diagram showing why we can't rotate around these bonds, because this p orbital here is interacting with that one with that one, which prevents rotation around this. This one is going to be interacting with that one and this one with that one, and so we can't rotate around that bond there. And so that's what makes that a chiral molecule, even though it lacks any chiral centers. All right, so I'm also going to introduce us in this video to what's called Fischer projections, which is a nice way of looking at stereochemistry. And so the rules for this is that we always have the wedged lines drawn horizontal, so looking like this right here. So these wedged lines here are horizontal. The dashed lines are always vertical, so this one right here and this one right here. So that's how we draw the Fischer diagram there. And so the rules of how we can actually manipulate these in space. So rotation by 180 degrees on the plane of the page is allowed. So moving this one right here to the down position, this one then going to this up position and interchanging this hydrogen and this hydroxide here. So that is an allowed move when we're using these Fischer projections. But rotation by 90 degrees is not allowed, and that's because we would end up with this one right here. We'd end up with these dashed lines on the horizontal and the wedged lines on the vertical. So if we rotated this by 30 or 90 degrees, we would end up with COOH, and this would be our dashed line. We'd end up with our wedge line with the H up there. We'd end up with this CH3, so H3C, and then this wedged one here, which would be our OH. And so that would break sort of these rules right here. And so this one is not allowed. So rotating by 90 degrees is not allowed. Similarly, rotation by 180 degrees perpendicular to the plane of the page is not allowed. And again, that's because we end up with the with these wedged ones here in the vertical positions and these dashed lines here in the horizontal, and so that breaks these two rules right here. And so, yeah, this is just the Fischer projection. It's just another way of trying to portray molecules that are three-dimensional in two dimensions. And so, that's what a lot of these projections are. Like the Newman projections we have been using as well are just another way of trying to portray three-dimensional molecules in two dimensions. And, the reason we have these different projections is because they can be useful in certain contexts. And so, that's really the only reason we have them. There's not, anything more than just because they're a useful tool. All right, and so with these Fischer projections, so I've been saying that the wedge lines are always horizontal, the dashed lines always vertical, but you oftentimes see them without them explicitly shown as wedged and dashed. And so you often see Fischer projections looking like this, and it's just sort of implied that we have the wedged and dashed lines. So What we have here is shown with the wedged and dashed lines explicitly. Then over here, I have this equal sign here to show that these are the same thing. We just have it shown like this without the wedge and dash lines, but it's just implied. We just understand that if these are Fischer projections, then the horizontal ones are sort of pointing out of the screen and the vertical ones are pointing into the screen. And so that's just another one of those conventions you have to get used to in organic chemistry, that we have this Fischer projection, which is this nice tool that we're going to be using here, and then we have this convention of sort of suppressing what the Fischer projection is actually showing, and just sort of understanding that that is the way that it's supposed to look. And so again, that's just one of those things you have to get used to. And if you don't like it, I would I really don't know who you would complain to. Maybe the IUPAC, but it certainly wouldn't be me that you would complain to, because I didn't choose for things to be this way. But you just have to get used to it. And so one of the reasons that the Fischer projections are nice is because they are great for finding internal mirror planes of symmetry. And so we have this structure here, this 2s3r23 dibromobutane. And so we see if we take the mirror image of it here, so we could see that if we just rotated this around this way 180 degrees, which we know is valid, is a valid move with our Fischer projections, then we just get this structure right back out of it. And so we know that this is not a chiral molecule, even though it has these two chiral centers in it. But of course, we wouldn't even have to go through this whole exercise, because just from the Fischer projection, we can see that this has an internal mirror plane of symmetry, and we already have established that any molecule with an internal mirror plane of symmetry is an achiral molecule. All right, so we also need these R and S conventions using the Fischer projections. And so I said in an earlier video, when I was talking about the R, that you could think of R as being sort of like the righty-tighty if you don't like the clockwise, counterclockwise thing. And it's the Fischer projections that I hinted at where this doesn't really work anymore. And so if we look at this, so if we're looking at just our 3D molecule the way we usually draw it for the RS thing, so we have our lowest priority atom here pointing in the back. This is R because this is going in the clockwise direction, so we know this is R. But if we are looking at it with our Fischer projection, it's actually the opposite. So with the Fischer projections, we actually go in the opposite direction. So now we are going counterclockwise around this. And so this is still R, because this is still the same molecule here. And so this still ends up being R. And I tried to draw this sort of three-dimensionally right here. And so we see, if we're sort of looking at it from inside the screen, but sort of at a slant, looking at it this way, we see that this would still be sort of going in the R direction for us, because this is our highest priority here, because it's just an oxygen. This is the second because we have a carbon, which will be double bound to this oxygen, because this is an aldehyde group. So an aldehyde group looks something like that. And so we have this carbon double bound to this oxygen. Then we have to go around to this one right here, which is just a carbon single bound to an oxygen. So that's our lowest priority. I don't know if this picture does a good job of portraying what I'm trying to show in 3 dimensions here. If we're looking sort of obliquely from inside the screen at this, we would have this be sort of to our left, I guess. This would be pointed up, and this would be sort of pointed down and to the right. And so we're kind of going in that clockwise direction there. But the take-home message here is that when we are looking at Fischer projections, our R and S designation is actually going to be the reverse of what we do when we're looking at these 3D molecules with our lowest priority atom pointing away from us. And so that sort of righty-tighty thing doesn't work for this anymore. So just remember, when we're doing Fischer projections, R and S is opposite. All right, and so that's just our introduction to Fischer projections. And Fischer projections are something along with Newman projections and other types of projections that we will be using, and we'll use those throughout the rest of organic chemistry. Like I said, they're just tools for different ways of trying to portray three-dimensional molecules in two dimensions that can be useful in certain contexts. All right, but now changing gears a little bit, we're going to be looking at diastereomers. And so remember, these stereoisomers are things that have the same number of atoms, the same number of bonds, and if we're not talking about conformational isomers, if we're just looking at these stereoisomers, then we have all of the same atoms bound to all of these same other atoms. They are just oriented different in space. And so one kind of diastereomer that I've already talked about quite a bit in these videos are these cis and trans isomers. And so we have all the same atoms between this and this. We have the same number of bonds, and all the atoms are bound to the same other atoms, but they are oriented different in space. So this has the methyl groups going that way, this one has this one down, and this one up. And so, yeah, I've already talked about those quite a bit. So now we have these Fischer projections here, and so in enantiomers, when we take a mirror image, we have R changing to S, and S changes to R. But in diastereomers, not all of them flip. So here we have this S changing to that R, but this S is just staying the same. And so these are not enantiomers because we are not changing the chirality of those chiral centers there. And so this right here is just staying the same. This H and this Br is staying the same between them, but now we are interchanging this chlorine and this hydrogen right here between the two. And so if like I said, in enantiomers, all of the R has to change to S and all of the S has to change to R. But in diastereomers, not all of them will flip. And so we can see here we have these two sets of enantiomers. So these are enantiomers. So we go from 2s3s to 2r3r, so both of those are flipping. Then these ones we have 2r3s going to 2s3r, so both of those are flipping. But any of these two here are going to be diastereomers of any of these two here. And so these two sets of enantiomers are diastereomers of each other. So we can see that's because between any two in here and any two in here, we are flipping one of the R or S, but not both of them. And so those are diastereomers of each other. And so what we see is we have, for this one, we have two chiral centers and four possible stereoisomers of each other. And so that brings us to this 2n rule. So a compound with n asymmetric carbons can have up to 2 to the n stereoisomers. And so we see up here with this 2-bromo 3-chlorobutane, which is what we're showing up here, we have 2 asymmetric carbons, and 2 to the second power equals 4 stereoisomers. So having 2 asymmetric carbons, though, does not necessarily mean having the full complement of 4 stereoisomers. And so we can actually see that here with the 2,3-dibromobutane, which has only 3 stereoisomers. And that's because we have these enantiomers here, so that's two of our stereoisomers. But then these ones right here are just the same compound. And so we'll actually see here in a few minutes that we call this a meso or meso compound. So these ones are called meso or meso, and that's because they have this internal plane of mirror symmetry here. And so we only have three possible stereoisomers, these two right here, and then this one right here. And so like I said, when we have n asymmetric carbons, it can have up to 2 to the n stereoisomers, and so it can't have more than that, but it can have less than that. All right, so let's move over here. All right, so enantiomers have the same physical properties as each other. So remember, enantiomers are mirror images, and they will have the exact same physical properties, except, of course, their interaction with plane polarized light. But their melting and boiling points will be the same, their solubility will be the same, their polarity will be the same. And so we can see how that would make them difficult to separate from each other. If you wanted to get a pure enantiomeric mixture from a racemic mixture, it would become difficult to try to separate them because we have to use these physical properties to try to separate them. Diastereomers, on the other hand, have differing physical properties, and so if we look at this trans 2-butene with cis 2-butene here. So the cis has these in the same direction, and so it actually has a vector sum dipole that actually increases the boiling point to 3.7 degrees Celsius, where the trans 2-butene, the bond dipoles cancel, and so our boiling point is only 0.9 degrees Celsius. Then if we look here at these 2,3-dibromosuccinic acid, when we have these two here, these are enantiomers of each other, and so we see that these both have the same melting point of 158 degrees Celsius. But then when we have the diastereomer of them, so this one is 2R, 3R, and the other enantiomer is 2S, 3S, and the diastereomer is 2R, 3S. Or it could be 3s2r, those would be the same thing. This 2,3-dibromosuccinic acid, our melting point actually goes up by almost 100 degrees Celsius, and so it's a pretty significant increase in the melting point. So the physical properties of it going from between these diastereomers is quite significant here. So we can also see this with glucose and lactose. So glucose has this hydroxide group pointing this way. The galactose just flips it to the other way. So this C4 hydroxyl group. So we go from D-glucose to D-galactose. In biochemistry, we call these epimers, which is just a fancy word for these type of diastereomers in sugars. But anyway, so glucose has a melting point of 148 degrees Celsius and galactose of 167 degrees Celsius. And so again, just showing that these have different physical properties. This is the meso compound thing. So achiral compounds that contain chirality centers, when we have these internal mirror planes of symmetry, so that these are just these two things are just the same compound. So we can call one 2R3S and one 2S3R, but that's just the numbering convention. These are the same compound, and so instead of listing them as two different compounds, even though they're the same compound, we can just call it meso 2,3-dibromobutane, and so that is what the meso compound thing is. All right, so I hinted at this above, so this separation of enantiomers, so trying to get a pure enantiomeric mixture, is called the resolution of enantiomers. And so biology does a really good job of this, and I discussed this a little bit in a previous video, that enzymes from biological organisms select for pure enantiomers. And so this can sometimes be exploited for making pure enantiomer compounds. So you can maybe have like a bacterial colony if you want, making a compound for you. So you can, sort of transform it with like a plasmid that has all of the requisite enzymes for making the compound you want, and then you can just purify that compound out of your bacteria. And so then you can use biology to actually obtain a pure enantiomer. But we also want to be able to do chemical resolution because we might not always have the enzymes for making the compound we want. And so if we want to make sort of, these novel compounds, which is something you often want, say, in like pharmaceuticals, then you want to be able to chemically resolve these. And so this is using a so-called chiral probe or resolving agent to separate enantiomers in a racemic mixture. So yeah, again, these are just some biological molecules here. So like our glucose is always the D here, or our sugars are always the D sugars in biology, and our amino acids are always the L sugars here in biology. Then we also use this L-tartaric acid, which I believe is something that is made by winemakers. I think it's a byproduct of wine making. And so that can actually be used because this is, well, we'll get to that here. All right, so enantiomers, like I said, have the same physical properties such as solubility, melting and boiling points, and so on. And diastereomers have different physical properties. And so to resolve enantiomers, we can simply turn them into diastereomers. And so what we want to do is actually uh, bind it to something else to turn it into a different molecule with it attached. And that different molecule, the product of that will be diastereomers of each other based on whatever enantiomer attaches to that other molecule. And so this is just a simple esterification reaction right here. I haven't really talked about that yet. We'll get to esterification reactions in future videos, but we're essentially taking this alcohol here and attaching it to this carboxylic acid here to make this, and it gets rid of water here. And so we're going to do that here with our tartaric acid. So remember I said that is this enantiomer here. And so if we want to separate our 2-butanol, or this butan-2-ol, so the S-butan-2-ol and R butan-2-ol, we bind these to each other, so we have our Fischer projections right here. And so remember, this is sort of pointing back into the screen here. Well, no, this is the wedge here on the horizontal here, and so this is also a wedge right here on the horizontal. And so this right here is the dash, this is the dash, this is the wedge going to that hydrogen. Same up here, we have the wedge going to that hydrogen. And so these two things, this one right here and this one right here, are diastereomers of each other. So these are diastereomers of each other. And so we can use the differing physical properties of these two molecules to separate them from each other. And then we can once we have the pure mixtures of the diastereomers, we can just do a chemical reaction to detach these from each other, and now we have our pure S-butan-2-ol and another one that is our pure R-butan-2-ol. And of course, these two things are different molecules here, and so we can use their different physical properties to separate them from each other to get a sort of pure butan-2-ol solvent and a pure butan-2 or R-butan-2-ol solvent. So yeah, the diastereomers can be separated by physical properties using techniques such as recrystallization, which exploits differences in solubility, chromatography, which exploits differences in polarity, or distillation, which exploits differences in boiling point. But if you already have, some pure enantiomer of something, you could actually use that to then separate out the pure enantiomer of something else. I mean, in a way, that's kind of what like biological enzymes are doing, because the enzymes are going to be chiral molecules, and so they're going to be selective of chiral molecules. But you could do that with chromatography as well. And so if we have our chiral column here, so this is our column which has beads with a chiral molecule bound to it, it's going to interact with the chiral molecules in our mobile phase right here differently. And so as those move down our column, one is going to move slower through it than the other. And so we have our one enantiomer going through slower than the other, and so we can actually separate those out. If we already have something that contains these sort of pure enantiomers here, so one enantiomer out of the two enantiomers possible. All right, so then conformers, I've already talked quite a bit about this, so I'm going to kind of go through this somewhat fast. So uh, we have the conformers here. Well, these are actually called rotamers here, which is just sort of a specific kind of conformer, but it's a rotamer because we're sort of rotating around a bond here. And so remember, we can have the totally eclipsed, which has the two bulky groups sort of eclipsing each other. We can have the gauche staggered. We can have the eclipsed, which is where bulky groups are eclipsed with non-bulky groups. And then we can have the anti or fully staggered here. And so the reason that we have these, that like the fully staggered, for instance, is going to be it's going to be the most stable one. Uh, so the biggest reason, so I talked about angle strain, which actually has more to do with these ring structures like the cyclopropane here and the cyclobutane here. So I'm not going to talk about that too much, but remember that's just moving away from preferred bond angles. And then we have the steric strain, which is the one that I kind of mostly referenced in my previous discussions of this, where these bulky side groups here are sort of getting in each other's space, and so that's going to be less stable. And so we want these bulky groups to be sort of as far away from each other as possible. But the sort of strain I didn't really talk about is this torsional strain here. And so this has to do with the negative charge from bonds coming off from adjacent atoms repelling each other. And so the way we could think about it is, and so I put here that this is actually stronger than steric strain. So the way we could think about it is we don't want these eclipsed conformations like this and this, mostly because of that torsional strain. But the reason the fully staggered is more favorable than the gauche staggered is because of the steric strain. So we still have some steric strain going on here where we have less steric strain here. But it's between these eclipsed ones here are most of their instability is actually coming from that torsional strain. So yeah, these are the types of steric strain here. So in the boat conformation on this hexane, we have these two things interacting up here, as well as these eclipsed hydrogens down here on the bottom. And so that's what makes those boat conformations less stable than these chair conformations, where these chair conformations have what are called the diaxial interactions. And so if we have this bulky group here, that's going to get in the space of these other groups here, and so that's going to be less stable. But then we have the torsional strain here, and so if we have the fully staggered here, that is the most stable right here, whereas if we have staggered, then we have the bonds here. So the electrons from these bonds, which are negatively charged, are going to have these electrostatic repulsions from each other. And so that is actually going to be what makes these staggered conformations most unstable. Then, as I said, the reason that the gauche or the eclipsed ones are most unstable rather. And the reason that the gouge staggered is more unstable than the fully staggered is because of those steric strains. But anyway, that is what I wanted to talk about with this. So yeah, we get a plot of the energy that looks like this, where the anti is the lowest energy. These totally eclipsed are the highest energy. And so we always, molecules always want to get to the lowest energy possible. And so that's why it's going to mostly be in the anti or fully staggered conformation, or I guess rotamer in this case here. But anyway, I don't want to ramble too long. That, as I said, was what I wanted to talk about for this chapter on stereoisomers. I hope you found this video helpful, and I will see you in the next one.